Hello. Today's topic is variation, and it's a really simple topic. The problem comes up when students tend to assume it can't be this easy. It must be more complicated, and they complicate things. Don't. This is as easy and simple as it sounds. Variation is simply when two variables have a relationship that can be described in terms of one constant. All right, there's a relationship between two variables, and I can describe that in terms of just one number. One constant means one number. But because we don't know what the number might be, there's all different possible numbers, we use k as our general descriptor of that constant. All right, so there's only two kinds of variable relationships. There's direct variation, and direct variation is when the quotient, one variable divided by the other variable, is that constant. And you can imagine, I can multiply both sides of this equation by x, and it would look like y equals kx. So when they're divided, when the quotient equals the constant, and then we turn that into a graphing style, it was going to look like y equals kx. This is a linear equation. You've seen that. What's special about this? There's no b. Right? That's all we're talking about is a linear relationship where there's no b. That constant, as you can see, turns out to be the slope, and we're going to look at graphs about that in a second. Again, this is simply what we have as a direct variation. The quotient between these two variables can be described as one number, and that tells us all we need to know about their relationship. So maybe the quotient is 7, in which case it would turn out to be y equals 7k. Again, I mean 7x, I apologize. K is 7 in this case. That's the varying constant. Okay, the other type of variation relationship is inverse variation. Inverse variation, let's see. When you think of direct, means this constant tells us that as this one's getting bigger, that one's also has to get bigger to equal that constant. So inverse, they multiply together to make a single constant. So you can see as one's going to get bigger, the other's going to get smaller, but not in the terms of there being a negative slope. Their product will always be a single number, right? And so if we were changing that into a y equals form, we divide both sides by x, it looks like this. And you can see this is not a linear relationship. The most common error is people think inverse variation would simply mean a negative slope. But a negative slope would still be direct variation, just with a negative constant. Inverse variation means their product has a single constant. You can see this is not a linear relationship, and we're going to see what that graph looks like. So if the inverse variation has a constant of 7, it's simply saying that x times y equals 7. Two numbers multiply, they're always going to equal 7. All right, let's look at some graphs of what this would be like. Here I have the graph of a direct relationship, the direct variation relationship, where the constant is 3. Y over x equals 3, and we can see that graph. And I could rewrite it, multiply both sides by x. This is the same relationship, this second line. And if we graph that, of course, we can see it's the same relationship. And that looks much more like we're used to seeing in a graphing equation form. Again, there's no y-intercept, or the y-intercept is 0, I should say. The y-intercept is 0, and this constant also tells us the slope. So if I think of it in other terms, right, here, what happens if it's less than 1? But just change the slope. That constant is left. What if the constant is negative? What do all of these have in common? They all go through the origin and they are linear. Basically, any linear relationship that goes through the origin is a direct relationship. All right. What if instead of writing y over x, it's x over y? Well, in this case, this is still a direct relationship. It's not the way we usually write it, but we're still saying the quotient between two numbers is always a single number. And when I graph that, came up over here, you can see it's still a linear relationship that goes through the origin. The only issue is this constant now does not tell us the slope of the line. It's still a direct relationship though. Now let's look at inverse relationships. We'll close these up. And the graph of an inverse relationship where the constant is 3 looks like this. It's not at all linear. If you notice, there are two parts to this graph that don't connect. In this case, you can see in the positive versions, as x gets bigger, yes, y has to get smaller. And over here, as x gets smaller, going this way, y does get bigger. But it doesn't get bigger in a linear way because the product equals this constant of 3. What happens if it's a different number? Let's try 2 gets smaller. Let's try 0.5. You can see it's even, you might be able to tell it's even tighter. Let me put one over here instead. xy equals 5. Graph that. It's out there. And what if we have xy equals -4? Graph that. In this case, they're in the second and fourth quadrants, the two parts of this graph. Now that's as simple as it gets, but there is one last piece to add on. In both these cases, the inverse and the direct relationship, k cannot equal 0. So there's one constant that describes their product or their quotient, but that number cannot be 0. I'm sure you can think that through and realize why that is the case. That's it. When we ask about direct and inverse relationships, basically what the usual question is, what is the constant in this situation? What is the varying constant here? What is the varying constant here? And simply asking, is this a direct variation or an inverse variation? As simple as that.